So, in continuation of our lecture 13, we discuss another example of application of variational method. And this second example is again a very known example to us, and that is the hydrogen atom, which again you have solved in your PH 204 course. And we studied this hydrogen atom exactly. We solved the hydrogen atom Hamiltonian, and now in this example what we will do is that we will calculate the ground state energy, or better to say we will try to estimate an upper limit on the ground state energy of the hydrogen atom using variational techniques. So let us start with the Hamiltonian. The Hamiltonian is well known. This is minus h slash square by twice mu grad square minus e square by 4 pi epsilon naught 1 by r. In this expression, this mu is the reduced mass of the system, but as we have said many times that the proton is extremely heavy, therefore the reduced mass of the system can be thought of as equivalent to the mass of the electron only. Now, the first thing that we should note about this problem is that rotation is a symmetry here. So rotation is a symmetry in this problem. It is rotationally symmetric, and therefore this immediately implies that angular momentum is conserved. So that is the first point we note. Second thing which is important to note is that if we expand this del square operator in spherical polar coordinates, we can see that there should come a non-vanishing angular momentum which will give rise to a centrifugal barrier. By this, what I mean is that if you write down the radial part of this equation, the equation should look like minus h slash square by 2 mu d2 dr2 plus h slash square by 2 mu into L plus 1 divided by r square minus e square by 4 pi epsilon naught 1 by r, and this whole thing multiplied by the radial wave function is equal to E times u. So one important thing to note here is that this is your standard Coulomb potential. The standard Coulomb potential is this one. Let us write this V Coulomb. And also you note that this whole thing we also called in our earlier course that this is nothing but my effective potential. Therefore, we note that for the states in which there is non-zero angular momentum, the binding must be weaker because there is this extra term in this effective potential. Whereas the ground state is of course most tightly bound, that is known, therefore the angular momentum for this ground state must be zero, so that it must be completely spherically symmetric and hence can only depend on the radial coordinates. This is very important because, as I have stressed quite a number of times, that in using the variational techniques to solve quantum mechanical problems, it is very useful or very much required to figure out the form of the trial wave function. And the form of the trial wave function in this particular case needs to be decided by looking at the symmetry properties of the problem and by keeping in mind that we are looking at the ground state of the hydrogen atom and we know that in the ground state the angular momentum is 0, the L is 0, so that this ground state must be completely spherically symmetric, and hence it can only depend on radial coordinates. There should not be any angular dependence in the ground state wave function. Therefore, keeping these things in mind, we will choose our trial wave function just like in the previous example, trial wave function, by keeping all the above points, these 2 points. This should be psi. Let us denote this parameter alpha again, and function of r is equal to e to the minus alpha r square, with alpha is positive for bound state. For bound state we have positive alpha. Therefore, this is the form of the ground state trial wave function that we are going to use. And remember, this form has been decided upon by keeping in mind the symmetry properties of the ground state wave function as well as the symmetry properties of the problem. So now this is the ground state trial wave function, and this wave function, as it is visibly clear that it satisfies all the symmetry requirements of the ground state of the hydrogen atom, where this alpha represents a variational parameter. Now we come to the three-dimensional problem. The last problem that we have solved, the harmonic oscillator problem, was in one dimension only. So therefore, the first thing, as I said, there are 3 different steps. You first figure out what is the inner product of psi alpha, then you figure out what is the expectation value of the potential energy operator, and then what is the expectation value of the kinetic energy operator, and then finally figure out what is your expectation value of the Hamiltonian, and from that you guess you figure out the bound state or ground state energy, the upper bound on the ground state energy. So we will follow the same technique here. So first thing first, we will write this as psi alpha. That means this is basically a triple integral. d3r is there, psi alpha 0 star and psi alpha 0. But we know that d3r means this is nothing but 4 pi r square dr, because there is no theta and phi dependence. The theta integral from 0 to pi and phi integral from 0 to 2 pi will give me a factor of 4 pi, because this d3r is nothing but r square sine square theta d theta dr d phi, and this integration will finally give us 4 pi dr r square, and then e to the power minus alpha r square twice is going to give us e to the power minus 2 alpha r. Now here again we will use the standard integrals. This will be useful in the next few calculations also. So the standard integral that we are going to use is this one, 0 to infinity dx x to the power n e to the power minus alpha x square. The result of this integration from 0 to infinity is nothing but gamma n plus 1 divided by 2 divided by 2 alpha to the power n plus 1 by 2. And we will also remember the fact that gamma half, the gamma function, is given by square root pi. So these two things we are going to keep in our mind, that this is the result that we are going to use in many of these integrations. So here the limit of the integration is from 0 to infinity. Therefore we are going to use this standard integral formula. This is given by therefore 4 pi Here my n is 2, therefore gamma 2 plus 1 by 2 is gamma 3 by 2 divided by 2 alpha to the power 3 by 2. Now what is gamma 3 by 2? Gamma 3 by 2 can be written as gamma half plus 1, which is nothing but half gamma half. This is a standard formula that gamma n plus 1 is n gamma n. So we are going to use that formula, and then gamma half is known to us, it is square root pi. Therefore gamma 3 by 2 should be square root pi by 2. So this is 4 pi divided by 2 into half gamma half and then alpha to the power 3 by 2, which is nothing but, let me write it in this manner, 4 pi over 2, we write this as root pi by 2 alpha to the power 3 by 2. I want to have a factor of pi by 2 alpha to the power 3 by 2 because that will be useful in cancelling some factors in the final expression. So let me write it as, we have 1 square root pi and 1 pi, that means we have pi to the power 3 by 2 already. And if I incorporate this 2 inside this to the power 3 by 2, then I have to have another 2 upstairs. So this will be overall pi by 2 alpha to the power 3 by 2. So this is the result of this normalization factor. Then the next step, we are going to calculate what is the expectation value of the potential energy. That means we are going to do this integration d3r psi alpha 0 star into minus e square by 4 pi epsilon naught r into psi alpha 0 r. Now again you note that there is no theta phi dependence in this potential. Therefore we can simply write this integral. Theta phi integrals will give us just the factor of 4 pi. So we will have minus 4 pi e square by 4 pi epsilon naught, and then this will be dr into, there will be 1 r square from r square sine square theta d theta dr d phi, and then there is 1 by r from the potential, and finally e to the power minus 2 alpha r square. So that's what we are going to get. So this is finally going to lead us to this integral minus e square by epsilon naught dr into r into e to the power minus 2 alpha r square, which is very easy to figure out. This is e square by epsilon naught with a minus sign, and then this is going to give me, because n is equal to 1 and we have a factor of gamma n plus 1 by 2 and n equal to 1 means this is gamma 1. The gamma 1 means that this is 1. So gamma 1 divided by 2 into 2 alpha. So this finally is leading to minus E square by epsilon naught 1 by 4 alpha, but let us write this again in a slightly complicated manner. Let me introduce this factor of pi by 2 alpha to the power 3 by 2. Therefore, I must be having a factor of 1 by pi to the power 3 by 2, and also there should be a factor of 2 alpha to the power half and a factor of 2 outside. I hope I have taken everything into account. Yes. Okay. So finally, what if we calculate the kinetic energy expectation in this trial wave function state? This is minus h slash square by twice mu d3r psi alpha 0 star r, and then remember we are doing it in the spherical polar coordinate. So this is going to give us 1 by r square ddr r square ddr psi alpha 0 r. Now psi alpha 0 r is nothing but e to the power minus 2 alpha r. So here we get, again there is no theta phi dependence in any of these factors. Therefore, we will have a factor of minus 4 pi h slash square by twice mu integral dr into r square into e to the power minus alpha r square. Now we have a factor of 1 by r square ddr into r square, and then if we take the derivative we have a factor of minus 2 alpha, and then we have a factor of r, and then we have e to the power minus alpha r square. So this therefore is going to give us finally, because this minus sign here will cancel this minus sign here, so we have 4 pi h slash square by twice mu dr, this r square gets cancelled. We have 1 e to the power minus alpha r square factor outside, and then we have 2 alpha, and then ddr of r cube e to the power minus alpha r square, r cube e to the power minus alpha r square. So this is leading us to pi h slash square by mu dr e to the power minus alpha r square into 2 alpha. Now if we do the derivative, we have 3r square minus alpha r cube into 2r e to the power minus alpha r square. So that is what we are going to get finally. So if we simplify this further, this is going to give us 2 pi h slash square by mu. This term is leading us to 6 alpha r square. This term is leading us to 4 alpha square r to the power 4, and there is another factor of e to the power minus 2 alpha r square, and we have an integration over dr. Now again you see that there is this r square e to the minus 2 alpha r square and r4 e to the minus 2 alpha r square. So the standard integration results will apply here. What we will have here is this 2 pi h slash square by mu into, we will have 6 alpha, and then there will be gamma 3 by 2 divided by 2 into 2 alpha to the power 3 by 2 minus 4 alpha square, and we will have r4 e to the minus 2 alpha r square. The integration limit is from 0 to infinity. So this is going to give us gamma 5 by 2 divided by 2 into 2 alpha to the power 5 by 2. So now you have to do some simplification. I am not spending the time on this simplification. After you evaluate these things, for example, gamma 3 by 2, as you have seen, is nothing but half gamma half. Similarly, gamma 5 by 2 can also be evaluated. Gamma 5 by 2 can be written as gamma 3 by 2 plus 1. So this is going to give us 3 by 2 gamma 3 by 2. But gamma 3 by 2 is again half gamma half. So this is 3 by 4 gamma half, but gamma half is root pi. Therefore, gamma 5 by 2 is nothing but 3 by 4 root pi. So use these facts, substitute everything here. The final result that you will obtain here is 3 alpha h slash square divided by 2 mu into pi by 2 alpha to the power 3 by 2. So again you see that now if you try to calculate the expectation value of the Hamiltonian operator psi alpha h psi alpha, this is going to give you psi alpha t plus v psi alpha divided by psi alpha psi alpha. So you substitute everything that we have obtained in this expressions of expectation value of v, expectation value of t, and the inner product of psi alpha. We put everything back, and what we obtain here is the following. After doing the simplification, do the algebra please. 3 alpha h slash square by twice mu minus e square by pi epsilon naught alpha by 2 pi to the power half. Again, by the same argument that we had given earlier in the case of harmonic oscillator, or to that effect for any general principle or any general problem of solving quantum mechanical problems using variational method, the value of alpha, the minimum value of alpha required to minimize the expectation value of h, should be obtained by solving this. If you do that, we can clearly see that this equation becomes 3 alpha, alpha will no longer be there, 3 h slash square by twice mu minus e square by pi epsilon naught into square root 2 pi, and there is a half alpha to the power half factor there. So we will have 1 by root alpha is equal to 0. There will be 2 here. Okay, so this therefore will lead us to a specific value of alpha min, which will be mu square e to the power 4 by 9 h slash square, h slash to the power 4 2 pi cube epsilon naught squared. But remember, what was your Bohr radius a naught? Bohr radius a naught in terms of h bar square and epsilon naught and mu and e are going to be of this form, 4 pi epsilon naught h bar square by mu e square. So therefore, if you substitute, if you replace these quantities, alpha minimum in terms of A naught should come out to be 8 by 9 pi A naught square. Therefore, the expectation value of H with this minimum value of alpha, that means expectation value of H mean, let us denote this in this manner. This is going to give us 3 H slash square by 2 mu into 8 by 9 pi A0 squared minus, let me write it like 8 by 9 A0 square pi whole to the power half E square by pi epsilon naught root 2 pi. And now what we do is that we again write back the expression of, or replace the A naught in terms of this, and the final result that one obtains of this calculation is of this form: mu e to the power 4 by 4 pi epsilon naught whole square into 2 h bar square into 8 by 3 pi. This is what you will finally obtain. So here the only thing that you have done here again is that in getting this result, this line, you have replaced A naught everywhere using this. This was written in just to give you some hint, some idea of what this 8 by 9 pi or what this alpha mean is in a shorter notation. But we need to get some numerical values, so we would like to write this in terms of the hydrogen energy. But you identify immediately that this is nothing but your ground state energy of the hydrogen atom. So this is E1 into 8 by 3 pi. So this is nothing but roughly equal to 0.85 E1, and this is therefore 11.54 electron volt. So we see that 13.6 electron volt minus 13.6 electron volt was the ground state energy of the hydrogen atom. And using the variational method, what we have obtained is this number, which is I think I have a minus sign here, yes, which is slightly higher than the actual ground state energy. So this is slightly higher because it's negative, slightly higher than the ground state energy. Of the hydrogen atom. So this is exactly what I wanted to tell you, that you can guess the trial wave function, and if you can guess it really well, then the bound on the ground state is obtainable by just doing some kind of algebra. There is no complicated mathematics there. The drawback on the other hand is that although it gives us an upper bound, we have no way of knowing how close we are to the true eigenvalue in the absence of some experimental result. So unless one tells us the true answer, we have no way to know how close we are. However, you remember our first theorem in this context, which we stated at the very beginning of discussion of variational principles, which showed us that if the difference from the true ground state wave function is of the order of epsilon, then the difference from the ground state energy is of the order of epsilon squared. This is why variational method often does well. So we have obtained one example where we are very close to the ground state energy, but not exactly the same as the ground state energy. In the next class, we will solve another problem which will be much more interesting, because the exact result you will not be able to obtain by some analytical method. So you have to take help of some kind of approximation methods. So we will study that using variational technique as well as perturbation technique, and the system that we will study there will be the ground state of the helium atom.